this is the 29th lecture of the course on principles of behavioral economics. We have been discussing prospect theory. So, once we discussed the original prospect theory, then we started discussing the improvements that were offered, and they are called later the cumulative prospect theory, in short CPT. So, I also described or started describing how the later version or advanced version cumulative prospect theory offers improvements in compared to the original prospect theory, alternatively called OPT. We can also call it just prospect theory. So, I mentioned that there are particularly two aspects where it has contributed. One is bringing in nonlinear preferences, the second one is source dependence. Also, this new prospect theory or cumulative prospect theory allows incorporation of multiple outcomes in a prospect. So, we continue with our discussion on cumulative prospect theory. Talking about nonlinear preferences, the principle of diminishing sensitivity applies to the weighting functions, where it entails that the impact of a given change in probability diminishes with its distance from the boundary. In the evaluation of outcomes, the reference point serves as a boundary that distinguishes gains from losses. In the evaluation of uncertainty, there are two natural boundaries, certainty and impossibility, that correspond to the endpoints of the certainty scale. So, as you understand that any probabilities would be actually lying between 0 and 1 with the two endpoints inclusive. So, the boundaries are certainty when the probability is equal to 1 and impossibility when the probability is equal to 0. Similarly, these are the boundaries of uncertainty, and similarly the weighting decision or weighting functions also would be having this kind of boundaries. For example, an increase of 0.1 in the probability of winning a given prize has more impact when it changes the probability of winning from 0.9 to 1 or from 0 to 0.1 than when it changes the probability of winning from 0.3 to 0.4 or from 0.6 to 0.7. This thing we discussed also yesterday with an example of probability changing by 0.01, right, but the impact remains the same. So, what it implies is that diminishing sensitivity therefore gives rise to a weighting function that is concave near 0 and convex near 1. So, if I try to draw this curve with 0 here and 1 here. So, I have sort of a box where this is 1 and this is also 1, then what it says is that it is concave near 0 and then convex near 1. For uncertain prospects, the principle yields sub-additivity for very unlikely events and super-additivity near certainty. The function is not well behaved near the endpoints, and very small probabilities can be either greatly overweighted or neglected altogether. Katie suggested the following as a two-part power function of the value scale. So, this is how the value scale can be expressed, where we have x is the outcome, x raised to the power alpha for all positive outcomes, that is when x takes a value greater than or equal to 0, or we can say all non-negative outcomes, and when there are negative outcomes, then the value function takes the form minus lambda into minus x raised to the power beta for all x less than 0. Alpha is the coefficient of diminishing marginal sensitivity to gains, and beta is the coefficient of diminishing marginal sensitivity to losses. Lambda refers to the coefficient of loss aversion. We will also check examples where we can apply this value function. The functional form of the weighting functions are W plus P equals to this form, and W minus P takes a different takes a very similar form, but only difference is that the parameters are different here. Here it is gamma, and in for negative it is referred to as delta, where gamma and delta determine the curvature of the function and they are different for losses and gains. A nonlinear regression procedure was used to estimate the options, estimate the parameters of equations. The median exponent of the value function was 0.88 for both gains and losses, that is alpha and beta, in accordance with diminishing sensitivity. So, what they observed is that alpha equals to beta equals to 0.88. What it also shows is that the extent of diminishing sensitivity in the domains of gains and losses are same if the values of beta and alpha are nearly same. The median lambda was 2.25, indicating pronounced loss aversion, and the median values of the parameters gamma and delta were 0.61 and 0.69 respectively. So, the median value of delta being 2.25 implies that loss aversion was actually observed and loss pinched to 2.25 times more than the pressure that you would be getting from a gain. That is what at least PT or Kahneman and Tversky observed through their experiments. Similarly, for the weighting functions, gamma and delta values were obtained as 0.61 and 0.69 respectively. Now, as I previously drew, this is basically the shape of the weighting function. You can see this line is actually refers to W plus and this is W minus. The smooth curves can be interpreted as weighting functions. The inverted S-shaped curve is steepest near the endpoints and shallow in the middle of the range. So, it is concave here and it is steep, again this is steep here and convex, and this is shallow near the middle range. What does it imply is that there is diminishing sensitivity in the middle range, or when probability changes in the middle range, then the decision weights actually do not change in equal proportions, while there are overweighting for very small probabilities, and similarly there is the impact of certainty for very high probabilities. For both positive and negative prospects, people overweight low probabilities and underweight moderate and high probabilities. Thus, people are relatively insensitive to probability difference in the middle range. Tversky and Kahneman performed a study with graduate students to reveal their preferences in terms of certainty equivalence for a number of prospects. The results are shown in the following slide, but I just need to mention here that in the following slides we will be having values of certainty equivalence denoted by CEs and EV referred to expected value. So, you need to remember that certainty equivalence, if they are greater than EV, this indicates risk seeking for both gains and losses, while if CE is less than EV, this indicates risk aversion for both gains and losses. If CE equals to EV, then the individual is basically risk neutral. This table contains the empirical evidence. We have prospects here, followed by descriptions, then expected values, then certainty equivalent, the median values of certainty equivalence, and attitude towards risk. I just need to mention, or maybe you are supposed to recall from the previous slide, that when we have CE greater than EV, then that indicates risk seeking for both gains and losses. When CE is less than EV, this indicates risk aversion for both gains and losses. So, CE less than EV, we have risk averse, and CE greater than EV, we have risk seeking. So, these are the prospects. In the beginning, we have a prospect where one can win 100 with a probability of 0.95. This is of course strictly positive prospect with high probability. Expected value is 95, which we can obtain by multiplying 100 with 0.95 plus 0 into 0.05 of course is going to give us 0. The median certainty equivalent was observed to be 78. Now, following this, the individuals are on average are risk averse. Now, in a similar fashion, if we just consider the negative of that prospect where one loses minus 100 with a probability of 0.95, then again the loss probability is high. the expected value is minus 95, the certainty equivalent is minus 84, which means there is risk seeking since certainty equivalent is greater than expected value. Next we consider two prospects where the probabilities are medium. The first one is for gain and the second one is loss. Here you gain 100 rupees, here you lose 100 rupees, and the expected values would of course be 50 and minus 50. Again it is observed that the certainty equivalent is lower. So, you are basically willing to accept a lower amount in order to avoid this prospect, or this prospect is equivalent to this amount of certain gain. So, since the certain gain that you are asking in lieu of this prospect, this risky prospect is lower than the expected value of the risky prospect, we call them risk averse. So, again these individuals are risk averse, and when it comes to losses, then their attitudes are again risk seeking because certainty equivalent is greater than the expected value of loss. And finally, these are the two prospects where the probabilities are low. You can see that they are just 0.05. Again, in one is gaining 100, in another one is losing 100. The expected values are again obtained by simply multiplying 100 by its probability. So, it is 5 here and minus 5 here. Now, you can see that the certainty equivalent is actually greater than the expected value, which means here the individuals are risk seeking. So, this implies that when the probability of winning a larger amount is actually very small, then people would rather prefer that risky prospect as compared to a sure gain of a smaller amount. In a similar fashion, when we consider this, then there is this loss of minus 100 with probability 0.05, while you are going to lose minus 5 for sure, then people go for a certainty equivalent. The median value is minus 8. Since the median value of certainty equivalent is less than the expected value, here the individuals are risk averse. So, one example is just mentioned here that the subjects are prepared to pay an average of $78 to obtain an expected value of $95, showing risk aversion. So, through this empirical evidence, actually Kahneman and Tversky tried to establish their argument that they put forward in the cumulative prospect theory about individuals' attitude towards risk as reflected in the preferences empirically or through their experiments. Now, again we get back to the improvements offered by CPT. So, it is just summarized here. We compared it with the expected utility theory or EUT. The comparison can be under 3 dimensions, or we can consider 3 different aspects. First of all, the objects of choice. In expected utility theory, probability distributions over wealth are basically the objects of choice, while in cumulative prospect theory, prospect frames in terms of gains as well as losses. Then the second aspect or specification or dimension is a valuation rule. In case of expected utility theory, it is simply the expected utility as we calculate them, and in case of cumulative prospect theory, it is a 2-part cumulative functional. The first part has a value function or value scale, and the second is a decision weighting scale. And the third specification is the characteristics of the functions that map uncertain events and possible outcomes into the subjective counterparts. In case of expected utility theory, utility is a concave function of wealth and nothing more than that it says. So, it just says that utility is a concave function for both gains and losses. But cumulative prospect theory says that the value function is S shaped and the weighting functions are inverse S shaped. So, the value function would look like this for gains and losses, while the weighting functions we have already drawn, they are inverted S shape. This is the 45-degree line. The curvature of weighting function explains the characteristic reflection pattern of attitudes to risky prospects. Overweighting of small probabilities explains the popularity of lotteries and insurance. Underweighting of high probabilities explain the prevalence of risk aversion in choices between probable gains and sure things. and 2 the prevalence of risk seeking in choices between probable and sure losses. Risk aversion for gains and risk seeking for losses are further enhanced by the curvature of the value function in 2 domains. The pronounced asymmetry of the value function, which we have labeled loss aversion, explains the extreme reluctance to accept mixed prospects. The shape of the weighting function explains the certainty effect. The value scale Vx previously quoted from Katie's original work had r equals to 0. For r not equals to 0, the value scale then can be written as Vx equal to x minus r raised to the power alpha for x greater than equal to r, and Vx equals to minus lambda into r minus x raised to the power beta if x is equal less than 0. Now, you see that if r is equals to 0, then this form becomes x raised to the power. If r is actually equals to 0, then for x greater than equals to 0, Vx becomes x raised to the power alpha. Similarly, for r equals to 0, when x is less than 0, then Vx becomes minus lambda minus x raised to the power beta, right. And these are the value functions or value scales that Katie mentioned in their original paper. Now, here r is of course the reference point. We are now going to talk about an application. This was also Tversky and Kahneman's original work published in 1981, where they are describing one problem and they are described it in 2 different ways. So, the problem is of Asian disease. This is the first statement, we call it Asian disease problem. Imagine that the US is preparing for the outbreak of an unusual Asian disease which is expected to kill 600 people. Now, 2 alternative programs to combat the disease have been proposed. Assume that the exact scientific estimate of the consequences of the programs are as follows. If program A is adopted, 200 people will be saved. If program B is adopted, there is 1/3 probability that 600 people will be saved and 2/3 probability that no one will be saved. Which of the 2 programs would you favor? When people were asked, 72% went for A and 28% went for B. Now, let us just write down the prospect. The prospects are, prospect A is simply 200 because it states that if A is adopted, then 200 people will be saved. So, 200 will be saved with a probability of 1. So, that is why we do not need to mention anything. So, it is like 200 1 and 400 0. So, 400 people will die for sure and 200 people will be saved for sure. So, this is simply written as 200, right. And similarly, for prospect B or for program B, when program B is adopted, then there is 1/3 probability that 600 people will be saved, and we can always write that there is 2/3 probability that no one will be saved. So, as you know that we can write it explicitly and we can also drop it. So, this is how we would be writing prospect B. Now, the same problem when stated little differently, we call it Asian disease problem 2. The initial portions would be similar, that imagine that the US is preparing for the outbreak of an unusual Asian disease which is expected to kill 600 people. 2 alternative programs to combat the disease have been proposed. Assume that the exact scientific estimate of the consequences of the programs are as follows. Now, from here the statements actually change. If program C is adopted, 400 people will die. Again, 400 people are going to die for sure. If program D is adopted, there is 1/3 probability that nobody will die and 2/3 probability that 600 people will die. Which of the 2 programs would you favor? So, here it was observed that 78% preferred D while 22% preferred C. Now, if we compare statements 1 and statement 2, you would see that if I compare A with C, then A said that 200 people will be saved for sure, and C is saying that 400 people will die for sure. So, these are actually the same thing. Similarly, B said that 600 people will be saved with a probability of 1/3, while there is the probability of 2/3 that nobody would be saved. In a similar fashion, D says that if 1/3 probability is there that nobody will die. So, nobody will die imply that 600 people are going to be saved, and then there is 2/3 probability that 600 people will die. So, 2/3 probability that nobody is going to live, again it is the same thing, right. However, we would be writing D as 600 2/3, because here we are actually writing things in terms of how many are dying. So, this is actually not the prospect of D. Prospect D is actually written as 0 2/3, sorry, would be written as there is 2/3 probability that 600 people will die. So, if I consider how many people are going to die, then 600 people are going to die. So, 0 1/3 nobody is going to live, and 600 2/3 600 people are going to die. So, if I drop this 0 1/3, then I will be left with only 600 2/3. Similarly, C 400 actually implies that 1 and 0, sorry 200 with 0. So, that is why we would be just writing 400. Now, name a few effects that this problem portrays. So, in this we can see framing, certainty, framing effect, primarily because the way things are framed, the answers are changing though the implications are the same. Then we see certainty effect, there is a preference for certain positive certain situations. A is preferred because it is stated as 200 people are going to be saved for sure. There is reflection effect, because this is when the gains and losses are mentioned, they are just the reflection of one another. There is loss aversion, because of loss aversion people actually preferred to go for say A over B and then D over C, and then preferring A over B and then D over C also refers to preference reversal. Next, let us calculate the value functions using the functional forms and estimated parameters prescribed by the CPT and check whether it correctly predicts the expressed preferences or not. Now, problem 1 states the problem as how many lives saved. So, this is how, that is the gain frame, and that is how the reference point is 0. Problem 2 states the problem as how many die, the loss frame. So, that is why the reference point is R equals to 600. Now, how many lives saved, R is equals to 0, because when we begin the problem statement, then it initially says that the disease is going to kill 600 people. So, 600 people are going to be killed, 0 is going to be saved, and then we start looking for programs, alternative programs, how many are going to be saved. So, since it is a gain frame, it is a positive frame. So, reference point is 0. So, when there are no chances or there are chances of 0 or saving 0 life, then how much these programs are able to save, that is why the reference point is 0 here. Similarly, in the die frame, that is the loss frame, again we consider R as 600, because as mentioned that in the beginning it said that the disease is going to kill 600 people. So, here 600 is the reference, 600 are going to die. Now the programs, their interventions, how much basically they are going to cause losses, that is how it is being framed. Now, these are important points, because first of all let us consider or calculate value functions for problem 1. I have mentioned problem 1 here just for ready references. Now, given the prospects are repeated here. The value functions are, first of all we have value function for prospect A, that is since pi or w plus 1 is equal to 1, alternatively pi plus 1 is equal to 1, then it is already mentioned here. So, I do not need to multiply anything here. I have V 200, which is 200 raised to the power 0.88, because alpha takes a value of 0.88 and it gives us an approximate value of 105.90. If I consider the prospect B, then in prospect B there is 2/3 chance that nobody will be saved. So, V is equals to 0, and then there is 1/3 chance that 600 people would be saved. Now, here the reference point is also 0. So, since v is equals to 0, since reference is 0, we can always use the original KT framework, and then x raised to the power alpha, x takes a value 0, and that is why we will not be having this component anywhere. We just focus on this component. So, w plus 1 3 v 600. W plus 1 3 can be written as like this. Now, here this is gain frame. So, we use the value of gamma which is equal to 0.61, and this is the functional form of W plus multiplied by 600 raised to the power 0.88, and it gives us a value of approximately 67.24. Since V A equals to 1.90 greater than V B 67.24, A is preferred to B, and this preference is actually explained or justified by the functional forms suggested by the cumulative prospect theory. Now, let us consider the value functions for problem 2. Again, the problem 2 is reproduced here, and these are the prospects. Now, given the prospects, and here the reference point or reference value is 600. The value functions are, first of all, for C. Again, you know that W minus 1 is also equals to 1. So, we have V 600 minus 400, and this is now here when I have reference point and in the domain of losses, KT defines Vx as minus lambda into r minus x raised to the power beta. So, lambda takes a value 2.25. So, I have minus 2.25 here, and r minus x is 200. So, 200 raised to the power again 0.88, because beta is also estimated to be 0.88. That gives me an approximate value of minus 238.28. Now, considering prospect D, I have again two parts. So, 2/3 probability is there that all 600 lives will be lost. So, minus W minus 2/3 V 600 minus 600 plus W minus 1/3 V 600 minus 0. Now, as you understand that 600 minus 600 gives us 0. So, of course, this term drops out. I am left with W minus 1/3 V 600, because 600 minus 0 is 600. So, again this is the functional form of W minus 1/3. Here we are using the power 0.69, because delta is estimated to be 0.69 multiplied by now 600. Following this functional form is minus 2.25 multiplied by 600 raised to the power 0.88, and the value that we get is minus 160.43. Now, you see that value of D, which is minus 160.43, is greater than value of C, which is minus 238.28. That is why D is preferred to C, and again the cumulative prospect theory can explain the preferences that are expressed for these two different statements by individuals. So, with this I conclude the discussion on prospect theory. In the next module, I will be just briefly talking about the criticisms that are raised or discussed or observed in the literature against prospect theory. So, these are the references for this module. Thank you.